Welcome to VCE Master Academy. Today we learn one of the most powerful shortcuts in all of mathematics. It's called differentiation, and by the end of this lesson, it will feel like a simple, friendly machine. You feed the machine a curve, and it hands you back the gradient, the steepness, at every single point. One rule does almost all the work. Here's our goal. Differentiate any power of x. Differentiate any polynomial. Find the exact gradient of a tangent line at any point you choose. And read the famous notation dy dx without blinking. Slow and steady. Let's begin.
First, one word in plain language. Gradient just means steepness, like the steepness of a hill. A big gradient is a steep climb. A gradient of 0 is flat ground. A straight line is easy. It has the same steepness everywhere. One number, done. But look at the curve on the right. Near the bottom, it's a gentle stroll. Further along, it's a proper climb. The steepness keeps changing as you move. So one number can never describe a curve. That's why we need something better. The derivative, written f' of x, is not one number. It's a whole formula. Feed in any x value, and it tells you the gradient of the curve at exactly that spot. A gradient machine. And the verb for building that machine is differentiate. Differentiate simply means find the derivative. That's the whole job of today. Here is the star of the show. If f of x is x to the power n, where n is a positive whole number, then the derivative is n times x to the power n minus 1. Say it in plain words and it becomes a dance move. The power jumps down the front as a multiplier. Then the power itself drops by 1. Down the front, drop by 1. That's it. Watch it work. X cubed. The 3 jumps down the front, the power drops to 2. 3x squared. X to the 7. 7 jumps down, power drops to 6. 7. X to the 6. Two small helpers ride along with the rule. First, constants. A constant is just a fixed number, like 5 or c. Its graph is a flat horizontal line, and flat ground has 0 steepness. So the derivative of any constant is 0, always. Second, multipliers. If there's a number in front, called the coefficient, it simply stays and waits. Differentiate the power as usual, then multiply by the coefficient at the end. So 5x to the 4 becomes 5 times 4x cubed, which is 20x cubed. The 5 never went anywhere. It just watched, then joined in. First worked example, nice and gentle. 3 little functions, one from each rule. We're given x to the 5, the constant 7, and 3x to the 4. We want all 3 derivatives. The rules are on the board. Down the front, drop by 1. Constants vanish, coefficients wait. Part A. The 5 jumps down the front. The power drops to 4. 5x to the 4. Part B. 7 is a constant, a flat line, 0 steepness. The derivative is 0, gone. Part C. The 3 waits patiently. X to the 4 gives 4x cubed. Then the 3 multiplies in. 3 times 4 is 12. 12x cubed. Box all 3. If you can do these, you can already do most of this chapter, because everything from here is just these 3 moves in a queue. Now, bigger functions. A polynomial is simply a sum of power terms, like x cubed plus 4x squared minus 6x plus 2. Each piece is called a term. And here's the wonderful news. To differentiate a polynomial, you just walk along it, term by term, and apply the rule to each piece separately. The plus and minus signs stay exactly where they are. No drama. 2 spots where students slip. A lonely x is really x to the power 1. Down the front comes the 1, the power drops to 0, and x to the 0 is 1. So the derivative of x is just 1. The derivative of 6x is 6, and the constant at the end, that plus 2, disappears completely. Flat ground, 0 steepness. Watch for those 2, and polynomials are a stroll. Second example, the exact polynomial from the last board. 4 terms, waiting in a queue. We want the derivative of the whole thing. The plan, visit each term, apply the rule, keep the signs. Term 1, x cubed. 3 jumps down, power drops. 3x squared. Term 2, 4x squared. 2 jumps down, 2 times 4 is 8, 8x. Term 3, minus 6x. The derivative of x is 1, so this term becomes just minus 6. The sign came along for the ride. Term 4, plus 2. A constant, 0, gone. Stitch the survivors together, 3x squared plus 8x minus 6. Box it, 4 terms in, 3 terms out, and every single move was one you already knew. Third example, and a common exam disguise. 2x multiplied by a bracket. As written, this isn't a tidy sum of terms yet. It's a product. We still want the derivative. Here's the strategy, and it's the whole lesson of this board. Never differentiate into a bracket at this level. Expand first, so the function becomes an honest polynomial. Then use the term-by-term rule you already trust. Expand. 2x times 3x squared is 6x cubed. 2x times minus 5x is minus 10x squared. 2x times 1 is 2x. So, f of x is 6x cubed minus 10x squared plus 2x. Now the machine. 6x cubed gives 18x squared. Minus 10x squared gives minus 20x. 2x gives 2. Box it. 18x squared minus 20x plus 2. Expand, then differentiate. In that order, every time. Now we put the machine to work. A tangent is a straight line that just touches the curve at one single point, matching its direction perfectly, like a ruler resting against a bend in the road. Here's the key fact. The gradient of that tangent at the point where x equals a is exactly f dash of a. Feed the point's x value into the derivative, and out comes the tangent's steepness. That's what the gradient machine was built for. So every tangent gradient question is the same 2 steps. Step 1. Differentiate to get f dash of x, the formula. Step 2. Substitute the given x value into that formula. A formula, then a number. Watch it in action. Fourth example, a parabola, and we want the steepness of its tangent at x equals 3. We're given the function and the location. We need one number, f dash of 3. 2 steps, exactly as promised. Step 1. Build the machine. X squared gives 2x. Minus 4x gives minus 4. Plus 5 is a constant, gone. So f dash of x is 2x minus 4. That formula holds the gradient of every point on this parabola. Step 2. Feed in 3. 2 times 3 is 6, minus 4 is 2. The gradient of the tangent at x equals 3 is 2. Box it. Look at the picture. At x equals 3, the curve has passed its lowest point and is climbing, and a gradient of 2 means rising 2 units for every 1 unit across. The number and the picture agree, and that check takes 2 seconds in an exam. Now the 8R level question, and notice how it flips the last one around. Before, they gave us the x and asked for the gradient. Now they give us the gradient, 9, and ask, where on the curve does that happen? Same curve rules, reversed direction. And they want coordinates, which means x and y. Half marks live in that little word. The plan. Build the derivative, set it equal to 9, solve for x, then find the matching y values. Differentiate. X cubed gives 3x squared. Minus 3x squared gives minus 6x. Plus 4 vanishes. Set it equal to 9. Move the 9 over and divide everything by 3, and we get x squared minus 2x minus 3 equals 0. That factorizes beautifully into x minus 3 times x plus 1. So x is 3, or x is negative 1. 2 places on the curve share this exact steepness. Now the y values. From the original function, never the derivative. At x equals 3, 27 minus 27 plus 4 is 4. At x equals negative 1 minus 3 plus 4 is 0. So the points are 3, 4, and negative 1, 0. Box them. See the picture. 2 tangent lines, perfectly parallel, because equal gradients mean parallel lines. That's the idea the examiner is really testing. One last skill, and it's purely about clothing. Mathematicians write the derivative in 2 costumes, and exams use both, so you need to greet each one like an old friend. Costume number 2 is called Leibniz notation. If y equals x cubed, we write dy dx equals 3x squared. Careful with your eyes here. Dy dx is not a fraction of d times y over d times x. It's one single symbol, one package. Read it out loud as The derivative of y with respect to x. In plain words, how fast y changes as x changes. There's also d dx with a bracket. That one isn't an answer, it's an instruction. It says, differentiate whatever sits inside this bracket. So d dx of 5x squared equals 10x. And here is the only fact you truly need. F dash of x and dy dx are the same thing. Same machine, same rules, same answers. When x is the variable and y is the function, swap between them freely. Last worked example, wearing the new costume. Y equals 2x cubed plus x. Find dy dx and its value when x is 1. Notice, they wrote y equals instead of f of x equals. That's the signal to answer in Leibniz clothing. Two things to find. The formula, then a number. The machine doesn't care about costumes. Term by term, as always. 2x cubed. 3 jumps down. 2 times 3 is 6. 6x squared. Then the lonely x gives 1. So dy dx equals 6x squared plus 1. Substitute x equals 1. 6 times 1 is 6, plus 1 is 7. Box both. The gradient of this curve at x equals 1 is 7. Same skills as board 4. New handwriting. If the question speaks Leibniz, answer in Leibniz. That's the whole etiquette. Why does anyone care about gradients? Here's why. A car accelerates from rest, and its distance traveled is 5t squared meters after t seconds. After 1 second, 5 meters. After 3 seconds, 45. The curve on the right gets steeper and steeper. Now ask, how fast is the car going? Speed is exactly how fast distance is changing, and how fast something changes is precisely what a derivative measures. Speed is the derivative of distance, so differentiate. 5t squared becomes 10t. Same rule as always, just with t instead of x. At 3 seconds, the speed is 10 times 3, 30 meters per second. That's the gradient of the tangent at t equals 3, and you can see it on the graph. That gold line's steepness is the car's speed at that instant. So the speedometer in a car is showing you a derivative, calculated live, every moment you drive. This chapter isn't abstract, it's on your dashboard. Let's gather it all up. One rule runs the show. The power jumps down the front, then drops by 1. Constants differentiate to 0 because flat lines have no steepness. Coefficients wait, then multiply back in. Polynomials are handled one term at a time, signs untouched. And if the function arrives in brackets, expand first, then differentiate. For the gradient of a tangent, 2 steps forever. Differentiate to get the formula, substitute to get the number. And if they hand you the gradient instead, set f dash of x equal to it and solve. Leibniz notation, dy dx, is the same derivative in different handwriting. Read it as the derivative of y with respect to x, and answer in whichever costume the question wears. And the classic mark saver. When a question asks for coordinates, the y value always comes from the original function, never from the derivative. If any line up there feels wobbly, scrub back to its board. That's exactly what the video is for. Your turn. 5 questions, 1 per skill from today. Question 1. 2 single terms. Remember what happens to constants. Question 2. A full polynomial. Term by term, keep the signs. Question 3. A tangent gradient. Formula first, number second. Question 4. A disguise. Expand before you touch the derivative. And question 5. The ATAR one. Gradient 0, solve, then coordinates, which means x and y, both. Pause the video here and work through them slowly. Full answers are on the next 2 boards, but don't peek until your page is full. Understanding first, speed later. Let's check your work, slowly. Question 1, Part A. 4x to the 6. The 6 jumps down, 4 times 6 is 24, and the power drops to 5. 24x to the 5. Part B. Y equals 9, a constant, a flat line. The derivative is 0. If you wrote 9, or 9x, that constant snuck past you. It always goes to 0. Question 2. Term by term. 2x to the 4 gives 8x cubed. Minus 3x squared gives minus 6x. 8x gives just 8. And minus 5, the constant, disappears. 8x cubed minus 6x plus 8.
The most common slip here is the middle sign, so check yours now. Question 3. The two steps. Differentiate. X squared gives 2x, 3x gives 3. So dy dx is 2x plus 3. Substitute x equals 2. 4 plus 3 is 7. The gradient of the tangent is 7. If you got 7 by any other honest route, well done, but formula then number is the path that never breaks.
And the last two. Question 4. Expand first. 3x times x squared is 3x cubed, and 3x times minus 2 is minus 6x. Now differentiate. 3x cubed gives 9x squared, minus 6x gives minus 6. 9x squared minus 6. If you try to differentiate straight into the bracket, this is your reminder. Expand, then differentiate, always in that order. Question 5. Differentiate. 3x squared minus 12. Set it to 0 because gradient 0 means the tangent is perfectly flat. Add 12, divide by 3, x squared equals 4. And careful here, that gives two answers, positive 2 and negative 2. Forgetting the negative root is the classic lost mark. Now the coordinates, from the original curve. At x equals 2, 8 minus 24 is negative 16. At x equals negative 2, negative 8 plus 24 is positive 16. So the points are 2, negative 16, and negative 2, 16. Those flat spots are actually the turning points of the cubic, the top of the hill and the bottom of the dip. And that idea is exactly where the next lesson picks up. If all 5 landed, brilliant. If one wobbled, its board is a scrub away. Great work today. You started this lesson with a mysterious symbol, and now you own a machine. The power comes down the front and drops by 1. Polynomials fall term by term. The gradient of any tangent is one substitution away, and dy dx holds no fear anymore. Next lesson, we use those flat spots, where the gradient is 0, to find the highest and lowest points a curve can reach. Until then, you're mastering VCE Maths, one concept at a time. See you next time.